of Colorado Cattlemen's Ag Water Network, and I'm joined by Sarah Didrikson. She is also with Colorado Cattlemen's, and Sarah is in the background making sure this webinar goes smoothly. We are going to be talking with AJ Brown from CSU's Ag Water Quality Program and Greg Peterson of the Colorado Ag Water Alliance. And we will be talking about water quality results from mountain hay meadow monitoring. So for the last 3 years, CSU and CAWA have been involved in a water quality study at ranches in the Yampa, Colorado, and Gunnison River basins. And so we're going to hear more about what this monitoring and testing is revealing about water quality coming off of irrigated mountain meadows. So our main presenter is AJ. AJ Brown is an ag data scientist with Colorado State University's Ag Water Quality Program. He has a master's degree in agronomy and is also a certified crop advisor. He joined the Ag Water Quality Program at CSU about 4 years ago, so he's been involved from the very beginning in this mountain meadow water quality research. Now, the other person with us is Greg Peterson. Greg is the executive director of the Colorado Ag Water Alliance, and he's going to be kind of introducing the subject. Greg was instrumental in helping initiate this whole study and also securing funding for the project. So I think, AJ, we can go ahead and have you share your screen now. And while he's doing that, just a couple of notes. One is that this is kind of a technical presentation. And so instead of holding questions for the end, if you have a question, you can pop that in the chat or you can unmute yourself and ask. I think from time to time, AJ will take a pause. And so that'll be potentially a good time to ask your question as well, or you can wait till the end. We should have a little bit of time then. Another note, today's webinar is being recorded, and we will be posting that on our website at agwaternetwork.org, along with highlights of the webinar later on. So Greg is going to be starting us off, and I think, Greg, it'd be good to just explain the impetus for why this type of monitoring was important for the ag industry. Why did we need to better understand water quality related to these irrigated mountain meadows? So, Greg, if you're ready, you can go ahead.
Great. Thanks, Phil. Well, so why did we do this? Which was because when we started, we were honestly a bit worried. Is this the kind of work that we want to be doing? What do we have to gain? Right now in the state of Colorado, in terms of water quality, we operate under Reg 85, Regulation 85, and that affects all non-point sources of pollution, and that's stormwater, runoff from open space, and that includes agriculture. And we are in a period where we are unregulated, and instead we are encouraged to just voluntarily adopt best management practices. That's very different from a state like California, where it is regulated, and every year, every producer they have to fill out a form literally stating what inputs they're putting on their fields and get that approved on an annual basis. I think that we prefer the way that we're doing things in Colorado, but how do we tell the story of how well we are managing nutrients in our farms and ranches? We don't exactly have one big database that just says, oh, this is what everybody's practice is, and this is how good of a job we've been improving our practices over the past few decades. We have some modeling efforts, and those are helpful. And that's one way we're working on telling the story. And then the other way are these single sites, like in this study, where we are able to get farmers and ranchers to participate and looking at mainly nitrogen, phosphorus, and sediment. And then also trying to determine what kinds of practices help them keep fertilizer on the field, not just for the benefit of water quality, but just because it's so expensive. And in cow-calf operations, where your margins are not great compared to some other kinds of ag operations, this is your most expensive input. And you want to keep as much of that on the field as possible and being used by the crop. And going into this, we felt pretty confident, because when you talk about water quality management in row crops, one of the best management practices that comes up a lot is a grass buffer strip. So just a strip of grass at the end of a row crop field that could be 10, 20, 30 feet wide. And then that works as a filter. Well, when you think about it, if you have an irrigated hay meadow, isn't your entire operation a giant grass buffer strip? And shouldn't that be doing something in beneficial for water quality if we have all this research saying it's helpful in these other settings? And so we've been really pleased with the results. And I we couldn't have done this without the three families that we had participate in this project. And I they were great partners to work with, and we've really enjoyed working with them. And I know that they got a lot out of this too. That they really felt the opportunity. They got to play around with different kinds of practices, just to try to manage their fertilizer as well as possible. So I'm going to stop there. And but well, the other people we couldn't have done this out without with was CSU, AJ Brown and Eric Wardle. They did a great job. I mean, working with us, working with the producers, coming out and really trying to visit these sites multiple times to make sure that we got it right. And so really appreciate everything that they did. And AJ, I'll leave it to you.
Perfect. Thank you, Greg. I appreciate that introduction, and it's been a pleasure to be able to learn about these systems over the years. And I grew up on a small farm in Rocky Ford, Colorado, where we did row crop agriculture typically, and I spent a little bit of time doing some ranchy stuff. But this has been a wonderful project to just kind of see the breadth of Colorado agriculture in a relatively old style of system, if you will. And we'll talk about that a little bit, because one of the things we've learned is that although one of the oldest practices of Colorado is mountain meadow hay ranching, it is also an area where we can see a lot of innovation happening and what it's doing to the surrounding systems. And yeah, the three farmers or the three ranching families that we worked with, incredible people. Was so lucky to have that too. We're glad to be with real producers with real results, and not that it's the observational results are critical for the success of Colorado's water quality, I think. So great. With that, I'm going to go ahead and jump right in. So as Greg mentioned, the modeling is one component, but today we're going to focus about some edge of field water quality research, and that's these point samples that we talk about. And why us? Why CSU in general? Greg had this funding. He was working with CDPHE to get this, and so a little bit of background about us and our program. If you haven't had the spiel already, I know a lot of familiar names in the room already. But the Ag Water Quality Program is a effort. It's actually written in statute through the state of Colorado. And so it's comprised of three organizations. We have the Department of Ag, CSU, and the Department of Public Health and Environment. And together we make the Ag Water Quality Program. And so every time a producer or yourself goes and buys fertilizer, the fertilizer tonnage tax goes a little bit into our pot of money. And so we're funded through the state through that taxation. Additionally, pesticide registration fees, because it's not just about nutrients and Reg 85, it's also about groundwater protection and ag chemicals in general. So those also go a little bit into our pot. And so it's, in theory, the people that are using the chemicals are also the people paying to have research and good information about what they do to the environment and other users of our water. Both on the surface and the ground. So that's the spiel. And so Greg reached out to us, and we were happy to oblige to work on this because edge of field monitoring is kind of our expertise. We've been doing it for a while, and we're trying to be very helpful in informing regulations like 85 and other things to make sure that policy is always backed by good science. So a little more broadly, why monitor water quality in agriculture, though? Well, you know, water quantity is a huge issue. And water quality is kind of sneaking up behind it. And there are a lot of efforts to look at both. But what I will say is that water quality and quantity are being modeled whether you participate in the research or not. This is an image of one such model that was developed here at CSU. This is by a group called the One Water Solutions Institute. But basically, people like the state engineer's office, a lot of these governmental agencies, USGS, et cetera, they're modeling what's happening on these fields. And they're trying to figure out things like How much nitrogen should we expect from agriculture? How much of whatever, right? And so that's an example of this pie chart here of what total nitrogen is expected. In this case, this particular watershed is near Platteville, and it's mostly suspected to be sourced by wastewater treatment facilities. That's not always the case, right? And so we make these pie charts and we make these loads, and ultimately the people using these tools make decisions about what it means. And so we do our due diligence as a program to make sure that these models, because they're going to use them whether we participate or not, are going to be the most accurate models possible. And that means collecting as much data as we can get, because models are calibrated with real field data. And that's what we wanted to do here. We don't want to make mountain meadow hay policy without having good calibrated mountain meadow hay data. So that's also a great reason for those to participate and get involved. It's important that everybody jumps in and helps, because the more data that we have, the better the models can be, and the less impacted or the less harm potentially that can come from modeling a field, your field, if you were the one helping to make it better. So how do we do that? How do we improve these models? What does it even look like to get these kinds of water samples? Well, here's an example of what this looks like. So here's some sites that we've had around the state, including some of these mountain meadow hay sites. You can kind of see there's two main boxes here. We have this, we have a bigger white box, and inside that is a commercial automated water sampler. And that's kind of the golden standard. And we put that next to some sort of flume or way to choke the water so we know how many gallons go by. And this device measures the depth of the water as well as when to sample, and it samples at periodic intervals that we determine. Another type of sampler, for example, in the middle top image there for Gunnison, we have a much smaller water sampler, and that was developed here at CSU. It's called the low-cost water sampler, and that's because it's about $700 as opposed to $15,000, which is the setup that's commercially available. So once again, we run on tax dollars. We try to make our money go as far as possible to give the best bang for the public's buck. And this allows us to do a lot more research with one site, because 15 grand can eat up a research budget pretty quickly, but 700 allows us to easily scale up how many points we get to sample, answering bigger questions. But we don't do just mountain meadow hay. You can see some of these pictures are in row crop fields here on the eastern slope as well. And we've also done comparisons between the commercial and our CSU low-cost versions, just to make sure that we're all comparing apples to apples when we get our data. So once we collect these waters, once again, these fancy devices that are so expensive, they don't even tell you what's in it. They just collect water well, because that's already a hard enough science. You have to preserve your water, you have to refrigerate your water, all kinds of different things. But we take that water and we take it back to our lab, and then we process it for all these things listed here. So we're looking at nutrients, like all the forms of nitrogen, the forms of phosphorus. We have sometimes iron, selenium. We look at forms of salinity, like total dissolved solids, electrical conductivity, and then pH, right? So we try to get a good spectrum of what's in this water sample from the surface. And we have to use these laboratory methods, because other sensors that kind of can report some of these are really, they're not the true value. They're a proxy. We're using voltage to estimate it, but it's not really what's happening there. Taking it to the lab is the only way that policy should be informed with the most accurate methods, and that's kind of why we have to stick with that. These are EPA approved methods. And here's an example of what that can look like. So in the field, we talk about, I'm going to start diving into what makes mountain meadow hay unique. And to do so, I'm going to start in row crop agriculture. Here's an example where we did do a controlled study. This was one of our row crop fields, and we've been working on conservation tillage for 14 years on this field now, where we have different levels of tillage on these plots, and we collect the water running off. And on your right, you see a picture of what that can look like, where you have this chocolate milk colored water coming out of a conventional tillage plot. Well, what is conventional tillage in this case for row crop agriculture? We call it full diesel. I mean, every operation that's traditional in old farming, that's what we do. We moldboard plow, we disc, we harrow, we roller packer, we do all these different things. And it's pretty, I mean, it's good for a nice clean seed bed and nice clean irrigation rows, but it can also have detrimental effects for soil health and water quality. And so um, this is kind of what we've been looking at. And on the left over there, you have what happens when we take it back to the lab and look at the erosion. So these are wafers, they're filter paper that we take the water and run through it, and then the filter paper collects that soil to look at the exact weight of soil that ran off the field. And so the top plot there is that conventional tillage, super dark. And then if we compare it just visually, let me change the slide here. This is in our least tillage plot. So this is where, in this case, it's actually, we call it strip till. So a strip tillage regime is pretty low intensity tillage. There's like 6 operations as opposed to 10 or 12 to make the tillage happen all the way from harvest back up to seed bed planting again. And in strip tillage, the whole idea is that you only disturb the soil where the seed will be gone or seed will be placed. So just like 2 or 3 inches either side of the seed bed, as opposed to the entirety of the field on a blanket basis. And so visually, you can just see what that can look like. And there's things that are attached to those soil particles too. And that's why it's important. So it's a nice visual, but it's also a nice reminder that soil carries a lot of things. The original water filter was made from soil. And that's how we discovered how soil was unique in that it can accept both negative and positive ions. But this concept of tillage, why does it matter to mountain meadow hay? Well, here's a graph that kind of just shows us what runoff erosion can look like from really disturbed soil all the way to least disturbed. And you'll notice on the very right, the purple bar is that mountain meadow hay. So this was 2 years of data from all of our sites around the state where we had a couple different things going on, but we had conventional tillage, conservation tillage, that filter strip that Greg mentioned, which would be a smaller version of a whole mountain meadow hay field. And then we had the mountain meadow hay field. And so this is on a log basis. So that means if the conventional tillage had a score of 6 on average, that's and then the mountain meadow hay had 3. That's 3 orders of magnitude larger. That's the difference between 1 and 1,000 parts per million, right? So it's a huge difference. And so mountain meadow hay is really a low disturbed system. It's pretty much perennial plants. It's not like you're tilling it up out there very often. You're trying not to. So that's where we get into mountain meadow hay. And that's so before we even started putting sensors in the ground and things, we just kind of wanted to come in with this kind of mindset to say, well, what should we be even looking for in a low disturbed system? And that's, cue Greg Peterson and the Colorado Ag Water Alliance. We couldn't have done it without them. We couldn't have done it without CDPHE's help either. And so we had these sites chosen with producers and our sponsors to basically, we wanted to characterize what does a mountain meadow hay look like when it comes to runoff water quality, and then let's see if we can see about valuable BMPs to make it better if that is needed, right? And these farmers and ranchers were so eager to participate. I couldn't thank them enough. And the first site that we'll talk about as a good example is Gunnison. So in Gunnison, we've been monitoring it, all of these sites really from 2022 to 2024. And the setup is pretty typical in this fashion and such that at the inflow, we put one of our low-cost samplers. So that's the water going into the field. On the outflow, we try to use the standard commercial sampler, what we'll call an ISCO here on out. And so additionally, we take some soil samples at these sites to look at what's in the soil, because that has the potential to be a major factor in what comes off in the water in the runoff, right? So this is one example. And in the bottom right, you can kind of see this clipped map here where we have 2 blue points. On one end of the field is the inflow sampler. On the left side of the field is the outflow sampler. So you have this giant, this one was, I think, approximately 80 acres or something field where we just kind of let the water wander through, and then we try to capture what that water can look like. In this case, it was a mini river that we had to walk in and use river transects, if you're familiar, to determine what that flow could look like. The next site that we looked at is called Molina, and Molina is a town near Colbran, and also I guess the larger city would be Rifle or Debec. And It was a really cool opportunity because this particular operation was really high mountain meadow, right off the Grand Mesa over there. And same kind of setup. Inflow was a low cost sampler. Outflow was an ISCO. And this farm had some sprinkler irrigation as well, and side roll irrigation, whereas the Gunnison was just wild flood, just tarp dams and flooding of the field. So that was pretty interesting. Then finally, we have another site called Yampa, and this was near Yampa, Colorado, in the Yampa River Valley over by Steamboat. And as you can see, same kind of setup. We have an inflow and an outflow, and along the way, we just try to capture the water and see how it flows. And on the left picture there, you can kind of see how that water meanders through the field through the tarp dam kind of setup. It builds pathways and works its way, and we tried to put our ISCO at where that water kind of all went out before it exited the field. This field we did a lot of fun with, so I'm going to kind of zoom in on some of the projects because those collaborators were just really excellent, and there was a lot of cool opportunity at this one too. So now that you've seen, before I get into data and results and what all that means, I'm just going to take a brief pause. That's how we set up. That's where we set up. And so our objective, once again, was to have these sites, collect water from them as they irrigated, see what was in that water, and then we can evaluate after the first year if there was a need for intervention and what that intervention might be. So I'll pause just briefly to see if there's any questions about how we installed what we did.
No questions here.
Okay. Appreciate that. Okay, well, let's get into some of the cool things that we found. So I'm going to jump right into some trends that we saw in water quality. So this looks like a lot, but I'm going to digest it for you. So this is an a really good, this is actually just a few samples, and what you're looking at here is all the different analytes we tested for in a single sample. And I've taken all of the samples from the Yampa site in 2024 and put them as averages. And so these bars represent annual average concentrations of water quality parameters. You don't need to even understand, it might be a little hard to see even, and that's okay, because what you need to know is that pink means inflow, blue means outflow. So when pink is higher, that means what came into the farm was higher than when it left the field. And so I'm going to put it into context for you of what did the field do? The field absorbed, it released, or it had no impact. Those are your three options. So firstly, here's an example of something that was absorbed. This is called TSS. This is total suspended solids. This is that erosion, the chocolate milk we were just talking about. So our hypothesis was correct that Greg said, well, these are giant filter strips. And what does a filter strip do? It filters out solid particles, and then it tends to let soluble things through, like a coffee filter. And so in this case, TSS came in pretty high, and that was parts per million of erosion coming in from the neighbor's farm before it went on to this farm. And by the time it left the field, the concentration was significantly lower. And so that really shows that those solid particles were getting stuck somewhere in between the start and the end of that field, probably up in the grass areas and other areas when it was flooding through that field. An example of what a release looks like is TDS, so total dissolved solids. So if you can imagine, once I use that filter paper and I capture all of the solid particles on it, what's left is the dissolved stuff in the bottom of the jar. It's the water with stuff in solution. So if you boil that off, all that's left is what was dissolved in the water, and that typically is synonymous with salt. And so this is a very common thing, not just in mountain meadow hay, but in all of agriculture in Colorado, in that when you run water through an agricultural field, unless you're really in a salty situation near the border of the state, you tend to accumulate salt in your outflow. So, and the inflow on average was a little lower. This is 200 parts per million, and then it leaves the field at about 300 parts per million. So the field was releasing salinity. This is not surprising, and it's not a concern because it's also a really low level. 300 parts per million is about it's about 0.3 decisiemens per meter. It's not a water quality concern. And then finally, here's an example of something that it had no impact on, which we were actually surprised about. So this final box that I'm highlighting here is TKN, total kaldal nitrogen. Well, if you're unfamiliar with total kaldal nitrogen, what it is it's a measure of organic forms of nitrogen, and that's often seen as primarily residue, organic matter in the soil, and manure. And what we had thought, because of previous research in the filter strips that we've done around the state, is that when you integrate cows into the environment, TKN tends to go up. And TKN goes up because we think of manure being integrated into the system, and so the water dissolves the manure and such. But what we saw here was a non-statistical difference, right? So once again, the bars themselves look a little different, but the error bars are if those are different, that's when we're starting to look at significant differences. But in this case, they overlapped. So we were surprised to see that although this was a grazing ranch, I think the power of the vegetative perennial crop overtook that, because manure is primarily a solid. This TKN is primarily a solid form, and so it's getting filtered out by the coffee filter, at least in this case. That may not be all cases. The filter strip, it was not the case. So I think it's a function of how your field is shaped and what kind of irrigation that you're looking at. In that same field, we talk about, so obviously one of the concerns is like, well, agriculture uses fertilizer. So what do we do about that? And like, is that a problem? Well, on the bottom left, I'm going to point you at that first. Here is a different year on that same field. This is actually 2022. And that blue bar is an example of what a spike can look like. So between irrigation 1 and irrigation 2, the producer fertilized using pelletized 32 UAN or 32, actually it was 4600 urea, right? Pelleted urea, I think. It also had some triple phos mixed in. It was a blend. But so he applied it and then he put some water on it, and that's when you would typically see your highest runoff of nitrogen, for example. And we did. But what I will also say here is that the concentration that it averaged out at over the year was 2 to 3 parts per million. Now, for our groundwater colleagues in a lot of areas of Colorado, 3 parts per million of nitrogen in the form of nitrate is often considered ambient. It's just there. So not to say that this isn't because of fertilizer. I'm not saying this is ambient. I'm just saying that the level itself is not really a concern, and it's actually optimal because it illustrates that although we fertilized, the amount of nitrogen coming off of this field as it relates to other things that we measure in groundwater and water quality, it's still a very low number. I'm very pleased with that result because it's basically just showing that the water up in the Yampa and near these headwaters are already super clean, and this field didn't seem to be contributing much, even if it was a fertilization event. However, in the subsequent years, that producer learned there's options to even reduce it further. And so on the right picture, we're going to talk about isotope analysis. If you're unfamiliar with isotope analysis is where you take the weights of certain atoms and you can start learning things about where they came from. There's been a lot of work to look at nitrate fertilizer or nitrogen in general, and to see what the isotope tracers are, to see if we can see if it came from manure, if it came from soil, if it came from fertilizer, or maybe the rain. And so that's kind of what you're looking at here. And so I have these stars, and at the inflow water, we took a sample and ran it for isotope analysis, and we have it came back as like primarily soil and maybe manure. It could be septic, it could be rain, but it was not really hitting tracers of fertilizer. However, in the outflow on that year, we saw traces. It was pointing towards fertilizer, and so we looked at that and we were like, oh man, so it really is coming from the fertilizer. And when we showed this to the producer, they saw it as an opportunity. So let me explain. Fertilizer is something we can control. So if this came back and it spiked big time in manure or precipitation or soil, and we were still seeing these runoff numbers, that's not something that the producer can easily intervene and change. Fertilizer is something we can manage. We have ultimate control on it because we decide when and how to apply it. So in the subsequent years, he did different practices with it to change that, and we saw reduced spikes. So there are opportunities to look at this and to see if there's where your nitrogen is coming from. But I will also say that we're suspecting that some of this is coming from the soil itself too. But this field was also very interesting because we saw an opportunity with this fertilizer to integrate a modern agricultural practice. It's generically called precision agriculture, right? And so this producer was really excited, so excited actually by the end of it, she decided to buy a drone herself. And so we often use drone imagery to look at various things in our research sites. And in this case, we've had a few people work on trying to create a map of plant nitrogen over the field. And that's what you're looking at here. So I apologize if you're colorblind in this audience, but the left half of this field is primarily red, which indicates low nitrogen in the plants. On the right side, we had green, so high nitrogen in the plants. So although we're not done yet, it seems like one of these opportunities where we could start to do precision fertilizing. Like if you only had to drive over half your field instead of the whole field, you could save money on fertilizer and also not over fertilize the other part of your field, which could have water quality benefits. Now, I don't need a fancy tractor to do that. That was just a drone, and the rancher bought the drone after. So there's opportunity to do this kind of work even in old systems.
AJ, what's this resolution of that drone in terms of this imagery?
In this imagery, I wanted to say each pixel was approximately 1 foot pixel, 1 square foot. We
Why
flew
do you
it at
think there is so much variability across the field?
In this case, this variability I almost think is entirely driven by the way they irrigate. So there's a channel that kind of runs through. You can see in the bottom part, there's like a little green uh, like string that runs through some yellow. That's one of the irrigation channels, I think. And so when you dam it up and all the water's running from the right side to the left side there, I guess that would be east to west. I think a lot of that nitrogen is following with the water and being washed out, Phil.
Gotcha. Thanks.
Yeah, no problem. Um, Great. And so I just Mount Meadow hay, another thing that we learned about in all these fields, and these are soils unlike I've ever worked in before. I mean, uh, I think they need to be highlighted because in a lot of agriculture, we talk about Colorado soils being extremely dry and low organic matter, and we're all hyped up about trying to increase your organic matter for whatever reason. Well, I'm here to tell you that all four of the sites that we worked in have extremely high organic matter. I'm talking like the smallest that we observed was 4.3% to 11 point, and then the highest was 11.6%. That is, I mean, 1/10 of your soil is organic matter. That's huge. Most Colorado soils are lucky to have 2%. And so, what does this mean? On the one hand, this is a really positive thing because that makes these mountain meadow hay sites a really large carbon sink, right? Like you can store a lot of carbon in here. It's long term. It's really interesting. It's healthy for a lot of different reasons, lots of microbe activity and that kind of stuff. But it's not a silver bullet because what can also happen when you have high organic matter is that you actually have a ton of nitrogen and phosphorus that's just waiting to be let out, right? So it's storing it there in the organic forms. But if something were to happen, like a tillage event or even just water logging in this case, we suspect that some of the we saw this form of nitrogen called nitrite in almost all of our mountain meadow hay sites. So nitrite, unlike nitrate, has one less oxygen atom, and it only shows up when there's hardly any oxygen, and that's often in the case when you have water logging. So where's the nitrogen coming from? I mean, it's obviously in the form of nitrite because it's we have these waterlogged situations where we put water on these fields for weeks and then we collect it or whatever. So not much oxygen when you're buried in water. But at this particular site in Yampa, there was a shallow groundwater table too. And so we suspect at least a little bit, and it would require some future research to confirm this, but we think just every year that organic matter is releasing some nitrogen as part of normal nitrogen cycling. And so whether you fertilize or not, there was years that this producer didn't fertilize. We still saw nitrite. So where did it come from? We suspect the organic matter was releasing it. And so what can you do in that case? It's nothing once again at levels of concern, but it's something to be aware of. Like you are sequestering carbon, great. You're also now having a source for other potential nutrients. But generically, I'd say it's a really positive thing, especially for soil health and microbes and other reasons, right? So just some food for thought. There's not a silver bullet when it comes to BMPs. There's silver buckshot, and it's really case by case. Okay, before I'm going to pause there and answer some questions because now I'm going to talk about kind of a watershed level project that we happened to do while we were in the Yampa River Valley. So, any questions about some of these mountain meadow hay findings? Outstanding. Outstanding. Okay. So Yampa and Steamboat happen to be really close to this reservoir called Stagecoach Reservoir, and it's really in between the two, Yampa and Steamboat, and then Stagecoach is almost halfway between them. So it's a reservoir that region of Colorado really depends on for hydroelectric power, for recreational use, for industrial use, agriculture, a lot of different reasons. And lately, it's been kind of under a looking glass because every year it's starting to get what they call eutrophied. Algae blooms, it turns over, it smells bad. Not a great water quality kind of situation to be in. And they're wondering about what's causing it. And so part of our investigation was to have some water quality monitoring around the reservoir. And so we did some what we call grab sampling with water bottles. And these water bottles, we looked up the reservoir, in the reservoir, and downstream of the reservoir, and also at a downstream tributary called Morrison Creek. We also had another ISCO placed up on top of the hill that flowed into the outflow of the dam, and this site was actually to give us a baseline comparison. It's basically BLM land where there's no fertilizer, no irrigation. It's just a grass pasture on top of a hill, and sometimes they put cows on there, but not even every year. So this is what that background water quality looks like. Once again, don't get too caught up in the numbers, but these red lines that I'm putting all over the graph indicate how the Yampa site, which was a heavily managed field, compared to the background site on the same year. So if it goes over an error bar, that means it's not really significantly different, right? So in a lot of cases, what we saw is that the background water quality was very similar to the ranch water quality. And so what does that tell us? That once again, that kind of points towards my organic matter theory of nitrate coming from organic, natural, I guess, quote unquote, natural sources, as opposed to artificial ones like fertilizer or manure application or something like that, right? Because they don't apply manure there, it just shows up. So although this is not definitive, it is just a nice way to look at it, right? So what does a managed versus unmanaged site water quality look like on an annual basis?
AJ, why do you think that this last slide, the
Yeah,
orthophos went up each year from 22 to 24?
that is an interesting question, and I don't have a clear answer for you. I think some of that is that could be something to do with, I mean, once again, this is a function of a non-irrigated field, but I would have expected 2023 to be, I mean, that was by far the wettest year. So if I would have expected a flush effect, it would have been that year. But the trends are increasing. The error bars say don't trust it. So I guess what I'll say, Phil, is like I can't definitively say this is super different. But although it looks like it's trending upward, I think you'd want to do a more robust kind of sampling event to see if ortho P was the issue. Because ortho P is interesting in that it can also pop up when you just have an accumulation of non-ortho P. Ortho P is a dissolved form of phosphorus that likes to, it typically shows up when you have an abundance of phosphorus and the thermodynamics favor it for it to dissolve, because often it doesn't in soils. It likes to be in a mineralized form. So, we could be seeing accumulation of P from erosion, but there wasn't a whole lot of erosion happening. So I'm kind of stumped on that, Phil.
Yeah, I'm sorry to stump you, but that is interesting.
Yes.
And with more monitoring, it may become clear as to what's going on.
Mm-hmm. Mm-hmm. Yeah, I'll have to think about that and I'll get back to you guys. If you need that answer, we can dive in and try to see more. I'd probably look on an event by event basis and see if there was like any particular spikes that happened correlated with any events that we wrote down in our field book that might have biased these, but we tried to avoid that. These are pretty clean data at this point, so I would doubt that. Anyway, so this is also a lot of data, but I'm gonna walk you through this kind of like the water quality data prior. What this represents is each plot, SCA, SCI, SCO, et cetera, that represents where along the Yampa River it was taken from beginning to end. So SCA was above the reservoir, and that's what we'll start here. So we took a grab sample above it. And what we're looking at is nitrate nitrogen concentration. So the axis on the Y side is milligrams per liter or parts per million. So above the reservoir, for all 4 years where we did this from 21 to 24, we saw very little nitrogen, almost exclusively no detects. And then that flows into the reservoir itself. I wouldn't super call this representative because this was taken from a grab sample on the beach. But there was no detects there. And that was another thing to highlight is that the x-axis is day of year. So we go from, January 1 to December 1, and we try to sample at least every month over the summer from, April to October. And so there was very little nitrogen seen at the beach. Interesting, right? But all of a sudden, we go to the dam, and at the outflow of the dam, we have some seasonality trends going on here where we saw in the early season some nitrogen coming out, and then it goes down, and then it comes up again. I see. Okay, so really quick, I'm going to pause and just address two questions in the chat. So Angela asked, why did we pick selenium as one of our analytes? The answer to that is it depends on the project, but we've had enough projects now that are concerned about selenium in Colorado that we often just add it to see if it is something of concern. But there's several EPA HUC watersheds that are impaired for selenium. And so we often just throw it in there sometimes. And then the second question from Sri is, has this research been published either full in part? No, that's the next step. So this is pretty hot off the presses, and the end of this presentation, hopefully, we'll have some time to start getting this into some peer review articles. Okay, so we have the dam outflow. We have nitrate that didn't come in going out, and that has to do with, I think, mixing. The dam itself mixes from different depths of the reservoir, so that kind of points towards you're accumulating nitrate over time, and then you're mixing from the bottom and top where it might be settling. So we're not sure on that. That's going to take some limnology and actual reservoir characterization. So then the dam flows into similarly where the background site would be. That's next in line for the stream flow. A little bit of nitrogen going on there. Nothing crazy, but it is contributing when that has to be from erosion of some sort because there's no fertilizer. And then we have Morrison Creek, which is a tributary that comes into the Yampa River from a different location. And early on in the season, it had a big spike. So something to know about Morrison Creek is that it had a big fire upstream. And so that was an interesting part about it. We were trying to see if that was having water quality impacts, and it was. And then finally, we have a downstream ranch where it all mixed together. And so that's kind of what that looks like. And so without showing you flow, you can kind of see Morrison Creek dominated the trends because it has the most flow and concentration. So whatever happened in Morrison tended to characterize what was happening in the Yampa afterward. Same thing, we'll do it quickly with phosphorus. What you notice with phosphorus is above Stagecoach, there's kind of a baseline level. So around the 0.1 parts per million level, this is total phosphorus. It just kind of hovers around this level. And then you go to the beach, occasional spike at the end of the season. That could be like we sampled some algae or something too, but that's to be expected. That's when it's eutrophied. And then we have the outflow of the dam. I don't know, that big error bar gives me a lot of suspicion. I would say it's not crazy. It's kind of noisy. So I wouldn't say there's anything definitive happening there, but it does look like we're still around that 0.1 baseline. And then we have the background site where we have a little bit of an elevation. Instead of hovering around 0.1 for all 4 years, it looked like 0.2, 0.3. So concentration coming off the, erosion. Once again, there's lots of rocks to touched by this water. And then Morrison Creek, it has a spike later on in the season when you're, and I don't know what exactly causes that influx, but once again, the fire, this phosphorus was tied with total suspended solids. And so this phosphorus likes to attach to the soil, and the fire caused a lot of erosion. So that's what our theory is there. Then finally, the downstream ranch, in this case, actually, it was maybe Morrison Creek was, the flow was lower, but it kind of hovered back down to a baseline. So lots of mixed messages there, but really fascinating. And so if there's other people, this is great preliminary data to talk about bigger projects down the road if you want to collaborate. And then one final slide, and we're almost done. This is the last slide, and this site is an edge of field site near Steamboat, and it's actually just for primarily outreach and demonstration. So it's owned by I believe the city. There's a lot of nonprofits working here as well as CSU, but it's close enough to town that if we wanted to show people what an edge of field monitoring site looks like, we have it set up, and we do collect some water off of it every year. And it's been a fun opportunity, and we've had a lot of engagement from the community to collaborate. So great to be there, and we'll continue to do this site for the at least the next few years because we've had such good engagement from this community, even though the project is over for Mount Meadow Hay in theory. So let's bring it all back together. Okay, we're at the end. What did we learn? Summarizing all of this, Mount Meadow Hay can often act as vegetative filter strips. They reduce solids and runoff. They can help keep sediment-bound constituents in fields. So often that could be like certain types of pesticides, phosphorus, et cetera, but the soluble chemicals are marginally affected. They kind of zip right through, just like coffee. Fertilizer can spike nutrients and runoff, but it's often minimally because the systems tend to be deprived. And by that, I mean, they run on such thin margins already that the inputs they don't get to fertilize every year. And so the soil is often near a deficit every year. And so there's a large opportunity for these soils to attenuate any nitrogen that's applied. But there's some challenges in these systems too. So just like any other agricultural system, we tend to see salts accumulating from these systems. We can add nutrients if you don't couple that with better management, you'll probably see these spikes. And although it was very low, we can do better. We can do better than low. We can do a lot better than low, I think. And then finally, it seems to add nitrite, which is likely coming from these organic matters in the nitrogen cycling process, coupled with waterlogged conditions. So what can you do about that? You know, that you're not going to make your organic matter go away, nor would you want to. So that being said, some promising best management practices that were kind of tried, and we didn't get to dive in because of the length of this presentation, but one thing you can do is try some irrigation water management. So don't, a lot of these Mountain Meadow hay systems just put on water, run it for 3 or 4 weeks, and then it's done, and it's just constant water the whole time. Well, if you're able to fertilize and give it some time before you irrigate again, and like stagger that and actually make some irrigation sets, it seems that that's going to be a good, promising BMP here, because then you control where that fertilizer is going and allow it to stay in the field a little longer to be uptaken. Secondly, fertilizer setbacks. What is a fertilizer setback? That just means applying fertilizer away from the outflow. So if you apply most of your fertilizer upstream in your field, if you will, so near the inflow, it allows it to kind of work itself. Any excess will run off towards the part that you would normally fertilize. And then by the time it reaches the outflow, it should be zero. So you're just not fertilizing your whole field. You're setting it back from the outflow to give it a chance to soak in over there and bring it to the outflow. And then finally, this one is possible, but I wouldn't say that it's often economical, but controlled or slow release fertilizers are probably a really good bet here too. I just don't know if they're going to be worth their bang to the buck because these systems are so economically thin already. But anytime I can put a coating on some of these things to prevent water from just washing it away or taking it up into the atmosphere is usually a win. Okay. With that, I'm going to just discuss one more time that this research is challenging, just like farming and ranching. And here's a picture of one of my colleagues, Jake, staring at my OSHA-approved method of getting our water sampler up to that background site near Stagecoach, where we just bungee corded a bunch of stuff and ratchet strapped it to our four-wheeler. Super safe. And that's why we don't have all these data. This is why these models, we need to do our best to get these data, because it's hard to get and it's not easy, but yet we model anyway. We're not going to stop modeling. So it's best if we can all participate and be a part of this solution. And okay, now we'll do some questions. Here's actually that family and the drone flight. This is that family that bought a drone after we left. It's been great. So the collaboration is everything.
Yeah, I don't think it would have happened without any collaboration, and hopefully that continues with the ranchers. So a lot there. We've got a few questions, and we'll just jump right into those. Have you sampled any cores going back to Stagecoach Reservoir from the sediment that's behind the dam, just sediment in the reservoir itself?
Yeah, no, we haven't. So that's kind of that area of future research. I think what we've learned, and we actually, Greg and I had a talk in Yampa or in Steamboat not too long ago. And I think what these findings are showing is that we need to look at the reservoir itself and to see how much has accumulated over the years. And, you know, there is a chance that the sediment can be holding all of these nutrients. And because we're mixing, it's coming out through them. I'm not sure. But that's kind of bigger than what we can do as a team. Characterizing a reservoir is actually quite a bit of effort, and that takes a whole team. But CDPHE has a protocol for it, so I think Kanan is on the call. He could talk about it if you needed a protocol to do it. Great.
So another question, AJ, is just here we've focused just on the mountain meadow sampling, but you did at the beginning allude to the fact that there's a lot of other sampling that CSU is doing, again, for the data, not just to analyze for better understanding it, but also to inform models that you're continually refining. And so this question just goes to, okay, outside of mountain hay meadows, do you have any of this type of research going on down in the flatland where we've got 2% plus or minus organic material? And could you talk about that a little bit?
Yeah, absolutely. So our program, the Mountain Meadow Hay didn't start until 3 years ago. And so, but before that, we've primarily worked in row crop agricultural systems with a lot less organic matter and are less. There is, although some sites have had ranches and livestock, but primarily we're just talking monoculture row crop situations. And so we have a lot of data on that. And Tanya, if you would like to learn more about that, like how example a filter strip can help versus not, we'd be happy to share that with you. If you scan that QR code, goes to our website, our contact information's there, and also some of the things that we've worked on.
Oh.
What about nitrite? So the question is, did nitrite increase in the fields that weren't fertilized? Did you see any trends there
Yes.
in any way?
Yep, like I mentioned, we found nitrite present in the outflow of all of our mountain meadow haze fields at one point or another. So it kind of alluded to whether they were or were not fertilized. We kind of saw it. So that's another reason that supports maybe it's coming from the organic matter. I'm not going to stand here and say that's definitively what's happening, but as we've looked through these data, that's kind of the leading hypothesis that it might be a really interesting study afterward to look at fate and transport of nitrogen in these systems.
Yeah, I think it's surprising that all of these systems, regardless of whether humans are interacting with it or not, leak a little bit of nitrogen. And I remember years ago there was a study done in the Sonoran Desert, just a lot of cactus and everything else out there. Nobody's farming it or doing anything else, and they found that those systems actually leak a little bit of nitrogen.
Yeah, I think that's exactly right, and also not something to be. As I've done this more in my career now, I don't think it's something that's super surprising either, because just like salts, I mean, nitrogen and phosphorus come from natural sources as well. And so that's what's even harder to characterize, I think, than agricultural sources of non-point source is just natural. What comes off your mountain? These background data are really hard to collect, but I think we'd be surprised to see, depending on what that geology was, there's a significant amount of nutrients just coming off of natural occurring sources.
You mentioned the setbacks at the edge of the field is one way to attenuate if you've got a little bit of extra nitrogen, for example, maybe phosphorus that's moving through. as a way to reduce that before it leaves the field. When you just think about more broadly, AJ, what this research has revealed in terms of the value of these large pasture scale buffer strips, but even smaller ones. What do you see as an opportunity for ag being a solution in areas, especially where you've got a lot of municipal activity going on, where you've got a lot of nitrogen and phosphorus that is entering a system and then being diverted? In terms of what's the opportunity for ag to be part of that solution and cleaning that water up and maybe getting compensated for that?
Yeah, good question, Phil. I mean, kind of generically, what I comes to mind, which is hard to do in Colorado, is using water that has nutrients in it already, because that means it's already not yours anymore. But in this case, if these systems tend to be deprived in nitrogen and phosphorus, they would be great sponges to absorb it and use it in the pasture land instead of running off. Because oftentimes in these other systems like row crop, we have an extra because we're not willing to take a cut on yield for our corn. So we often have too much nitrogen at the end of the season because we're just going to over apply a little bit. That's not always the case, but I see it more often. This system seems to always run on a deficit because once again, everybody's running on thin margins and such. So if there's a way to get this water that's marginal for that reason to go through a field and not impact the farmer's crop health, right? Like we need to make sure it's also not going to ruin it for other reasons. But if it's purely because of nitrogen and phosphorus, like it'd be great to run through that field. I don't know how practical that is, but that would be an opportunity. I also think that encouraging these producers to continue to leave these sites just undisturbed. I mean, if we are concerned about carbon and things, like don't shake the boat with it, because these are managed systems that we're making good productivity off of, and they are honestly probably one of the largest carbon sinks in our state. So I think just to highlight that and be aware of that, I don't personally think that carbon crediting is going to be is a profitable option for most people, but being able to just find some way to give these producers merit for being able to do that and keep it in the soil is worth highlighting. And I'm not the policymaker on that.
Any other questions? We've got a couple more minutes.
Greg.
Yeah, less of a question and more of a just a share. As when we started this project, a group of farmers got word of it down in the Grand Junction area. And then they came to us and were just like, well, we want to do something similar to this. We're really concerned about increasing water quality regulation in that area. And we've wrapped up the first year of that. We still have 2 more years of that study. And I mean, it's just 1 year of data, but we've already been really excited about some of the results, especially with nitrogen stabilizers. And we're going to keep on working with those 4 farmers down there on that. But that's where I think and we're going to be also talking with the ranchers in South Routt County about this study, and just, is this something that more people are interested in? Because I think there's really, going forward, there's 2 reasons for us to keep doing this kind of work. And one is to show just the good management practices that people have been implementing and trying to capture that data, but then also of just a financial of just financially trying to figure out, okay, what are ways that you can keep this expensive input on your fields, and working with you on that. And I've been really pleased when we went to CDPHE and applied for this, both of those programs. I told them, we're not going to give you names. We're not going to give you locations. We're not going to tell you who's participating in this at all. And over both projects, everybody has come out and they're pretty public now about their participation. But it really gave us the comfort that we needed to go through with getting this kind of research.
Yeah, one of the things I think that's been so interesting about the data that has come out from these sites is that we look at points jumping around on a graph, and some of them are a bit high, and we think, wow, is that bad? But when you look at the scale on the y-axis, it's remarkable how low all of these levels are.
That's right. That's an important thing, Phil, to just recognize, because especially Mount Meadow hay, in cases like Stagecoach, I think it's far too easy for a community to turn and say, yeah, agriculture has fertilizer, so they're obviously the first problem. But without that data to show it, I think it's just an unfounded claim. It's always case by case. There might even be ranches that do have a source problem, but what we saw here on these situations is that they're typically not, because they are so low input. So it kind of just shakes the norm and makes you think, well, we need to dig deeper and see what's happening then.
Well, we're up against the end of the lunch hour, so we're going to wrap it up. Um, Thanks so much for all this good info, AJ. Really appreciate it. I'm sure you don't mind if people contact you. Same with Greg, if
By
they've
all
got
means.
questions or comments, thoughts. I know you guys are always eager to talk about this stuff, as am I. You're welcome to contact me. But really appreciate you guys taking the time to kind of inform us on this topic, and we'll see where it goes from here. One other note is that we have recorded today's webinar, and that, along with the highlights of what was covered, will be posted on our website at agwaternetwork.org. So with that, again, thanks for joining us today, and that concludes this webinar.
Have a great day, everyone.
Thanks, you too.